Suppose you have two linearly independent vectors in the plane. Using these two vectors, you can form a grid on the entire plane. And the grid gives you a way of visualizing how different vectors in the plane can be written as linear combinations of v1 and v2. For example, this point is 2 times v1 plus v2, because to get there, you have to go 2 steps in the v1 direction and 1 step in the v2 direction. Whereas this orange point is v1 minus v2, because to get there you have to go 1 step in the v1 direction and 1 step opposite to the v2 direction. And then this point here is 1/2 v1 plus 3/2 v2. So you can see that every point on the plane can be written as a linear combination of v1 and v2. And when we do that, we're basically treating v1 and v2 as axes in a new coordinate system. And similarly, if you have a plane through the origin in three-dimensional space, and if you have two vectors that are linearly independent on that plane, then you can use those two vectors to create a coordinate system on the plane. These are two instances of a general fact, which is that if you have a basis for a subspace, then that basis gives you a coordinate system on that subspace. So let's go through the details about how this works. So suppose v1 to vm is a basis for a subspace W. Let's remember what it means to be a basis. So the first thing that it means is that the span of v1 to vm is equal to W. And another way of saying that is that every vector W in the subspace can be written as a linear combination of the vectors in V. So that means that there exists some scalars, C1, C2, and so on, such that W is equal to C1, V1 plus C2, V2, and so on. And then the second thing that has to be true for the vectors to be a basis is that they have to be linearly independent. And another way to describe what it means to be linearly independent is to say that the only way to get 0 as a linear combination of the vectors is if all of the coefficients, the CIs, are equal to 0. Now there's a nice characterization that combines both of these things together into a single statement. And that's to say that every vector in W can be uniquely written as a linear combination of the basis vectors. So why is that? Well, the spanning condition tells us that every vector in W can be written as a linear combination of the basis vectors. And linear independence actually tells us that that expression is unique. And the reason for that is that if there were two different ways to write W as a linear combination of the basis vectors, then we could take the two equations and we could subtract one from the other, and we would get an expression where 0 is written as a linear combination of the basis vectors. But then linear independence says that this can only happen if the coefficients are all equal to 0. And so in this case, the coefficients are Ci minus Bi. And if that's 0, that means that Ci is equal to Bi, which means that those two different ways of writing W were actually the same way all along. So I would say that this condition, that every vector in the subspace can be uniquely written as a linear combination of the basis vectors, that's really what the French would call the raison d'être, the reason to exist. This is the reason that we talk about a basis in the first place. It means that we can treat the basis vectors as sort of like axes for the subspace. And then we can describe the vectors in the subspace in terms of coordinates along those axes. These coefficients, the CIs, are the coordinates for W in terms of the basis. So if you go back and look at the previous slide where I was drawing the grids, that's exactly what was happening. You look at a vector, you look at how to write that vector as a combination of the basis vectors, and then you get coordinates for that vector. And hopefully this can give you a better understanding of what spanning and linear independence mean. When we say that the vectors span W, what we're basically saying is that when you make that grid, the grid actually covers all of W. And then when we say that the vectors are linearly independent, what we're saying is that those grid lines, they don't overlap each other. They actually go in different directions. And so when you find where the vector is on the grid, it's unambiguous what the coordinates are for that vector. Okay, so suppose you have a basis for a subspace W of Rn. Sometimes it's convenient to just give a name to the entire basis so you don't have to keep writing out all of those vectors. And so I'm using a curly B to describe the entire set of vectors that forms this basis. We know now that every vector in the subspace can be uniquely written as a linear combination of the basis vectors. And then from this expression, we can form a vector that's called the b-coordinate vector of W, and that's the vector that's made out of those coefficients. So here's the notation for the b-coordinate vector. It's the vector with a square brackets and a little b subscript, and it's just the vector whose entries are C1, C2, and so on. Okay, so let's look at an example. Let's suppose that V1 is 1, 3, and V2 is 2, minus 1. Then these two vectors form a basis for R2, and I'll let you think about why. And the question is to find the b-coordinate vector of 4, 5. To do this, we would solve the equation C1V1 plus C2V2 equals 4, 5, where we're solving for C1 and C2. And if we put in the numbers for V1 and V2, then the equation looks like this. And surprise, surprise, like everything in this class, this is a system of linear equations. So we solve it by making an augmented matrix and putting it in reduced echelon form. And this is what you get. And from here, we can just read off the solution. C1 equals 2 and C2 equals 1. And those are the numbers that make up the coordinate vector. So the answer is that the b-coordinate vector of 4, 5 is 2, 1. And this equation has exactly the geometric interpretation that we were discussing at the beginning of the lecture, where in this case the vector 4, 5 is 2 times v1 plus 1 times v2. And so if you look at the grid that's formed by v1 and v2, you can get to 4, 5 by going 2 steps in the v1 direction and 1 step in the v2 direction. So the idea is that this basis, v1, v2, gives us a new coordinate system which we can use to address points in the plane in a different way. All right, so why would we want to do this? Basically, the idea is that if you're studying some kind of a system, you might be in a situation where when you use the regular coordinates, the system looks kind of complicated. But if you can choose coordinates in a nice way, where the coordinates are somehow adapted to the system, then the system can start to look simpler, and it can be easier to solve, it can be easier to study and analyze. We'll actually be doing this quite a bit later in the semester. But I'll show you one simple example of that later in this lecture. So the general case is actually quite similar to what we just saw in the example. So suppose that V1 to Vm is a basis for a subspace W. And suppose that you have a vector in W. How do we find the b-coordinate vector? Well, to do that, you would want to solve the equation C1V1 plus C2V2 and so on is equal to W. And this equation can be rewritten as a matrix equation, where the matrix has V1 to Vm as its columns. And to solve it, you would write down the augmented matrix that has the V vectors on the left and the W vector on the right, and then you put it into reduced echelon form to solve. So what could the reduced echelon form be? Well, we don't know anything about these vectors, right? So it could be anything, huh? No! We actually know quite a lot about these vectors. We know that they're a basis for this subspace W. And that means that they're linearly independent and that they span all of W. And that actually gives us enough information to pretty much say what happens with the reduced echelon form. So the fact that the columns on the left are linearly independent means that there won't be any free variables when you solve. That means that there's going to be a pivot in every column, and in reduced echelon form, having a pivot in every column means that you just have columns where there's a 1 somewhere and zeros everywhere else. In other words, you end up with something that looks like an identity matrix, but possibly with some rows of zeros at the bottom. In the example we did earlier, we didn't have those rows of zeros at the bottom because the number of rows was equal to the number of columns. But in general, it could be possible for the number of rows to be more than the number of columns, and then you'd have some extra rows of zeros at the bottom. Well then, because you have those rows of zeros on the left, is it possible that you have something non-zero on the right in those rows, making the system inconsistent? No! The vectors span W, So that means that every vector in W can be written as a linear combination of the basis vectors. And so that means that there does exist a solution. The system is consistent. And so that means that in the reduced echelon form, you're going to have zeros on the right that match up with the rows of zeros on the left. And the other entries on the right are the things that we're looking for, the C1 to Cm. And so that is where you find the b-coordinate vector for W. And so this is always how it works. And one of the things that's useful about seeing how it works and knowing that it works like this is that you can use it to detect when things go wrong. For example, if the v vectors were not linearly independent, then you wouldn't see the reduced echelon form having the identity matrix with rows of zeros on the bottom. And then you'd know that there's a problem. They have to be linearly independent to be a basis. And on the other hand, if the system were inconsistent, then that would be a problem, because that would mean that it's impossible to write W as a linear combination of the v vectors. There could be two ways that that could happen. Maybe the W vector is not actually a vector in the subspace. The other possibility is that maybe the v vectors don't actually span the subspace. Either way, that's a problem, and this process would detect that. So let's look at a special case of this, where the subspace is actually all of Rn. And so that means you'd have n vectors that form a basis for Rn. So then, following the same procedure that we just used before, if we wanted to find the b-coordinate vector for some vector W, we would solve this equation C1v1 to Cnvn is equal to W. So just as before, we would write down this augmented matrix and put it into reduced echelon form to solve. But the key difference now is that because there's n vectors in n-dimensional space, the matrix on the left is a square matrix. And so you just get the identity matrix in reduced echelon form. There's no rows of zeros. So you just have the identity matrix on the left, and then on the right, you have the b-coordinate vector for W. Now, let's use A to denote this matrix whose columns are the vectors v1 to vn. We just did some row operations that turned A into the identity matrix. And we know that doing row operations is the same thing as multiplying by elementary matrices, and that the sequence of row operations that turn A into I correspond to the inverse of A. So in other words, if we think of these augmented matrices as representing matrix equations, then on the left we have the matrix equation AX equals W. And on the right we have the identity times X is equal to this b-coordinate vector. And the process of going from the left to the right is actually just multiplying both sides of the equation by A inverse. And so what that means is that to get the b-coordinate vector of W, you just multiply W by the inverse of the matrix whose columns are the basis vectors. And the big picture takeaway here is that when you change from regular coordinates to b-coordinates and back, you're really just multiplying by a matrix that's invertible and its inverse. I like to think of this as a change of perspective. It's like you're looking at the same thing, but you're looking at it in a different way. And sometimes when you look at the same thing from different perspectives, you see different things. So let A be an n by n matrix, not necessarily invertible, just any n by n matrix. Then, as we know, multiplying by A gives you a linear transformation from Rn to Rn. And then suppose we have a basis, v1 to vn, for Rn. Now, if I have a vector x, I could multiply it by A and get A times x. But I also could rewrite it in the coordinate system that comes from the basis. And based on what we just discussed in the previous slide, we know that you can go back and forth between x and this coordinate vector by multiplying by an invertible matrix and its inverse. And to be more specific, if we let P be the matrix whose columns are the basis vectors, then P is the matrix that turns the coordinate vector back into the original vector. So we can relate x to its coordinate vector by P, but we could also relate A times x to its coordinate vector. And remember, we're taking the philosophy that the coordinate vector is just the original vector from a different perspective. we could look at the entire process of going from the coordinate vector for x to the coordinate vector for ax as giving us a way to look at A from a different perspective. So we'll call that the coordinate matrix of A. So what is the coordinate matrix of A? Well, just by the way that we've constructed it, it's the thing that gets you all the way from the lower left corner of this diagram to the lower right corner of the diagram. And we can get there by going up and then over and then down. And the coordinate matrix of A just shortcuts that process and gets you there in one step. We've seen this sort of thing before. This is exactly how matrix multiplication works. So the equation that comes from this diagram is that the coordinate matrix of A is P inverse A P. And I would say that the right way to think about what this coordinate matrix is that it tells you what the linear transformation looks like from the point of view of this new set of axes given by the vectors in the basis. So we'll be using this idea a lot later in the semester, but for now I'll just show you one example so you can see the value of it. So let's look at this matrix A, and what can we say about it? Well, we know that the columns of A tell you where E1 and E2 get mapped. So we can draw a picture like this, but it sort of feels like there's not that much more to say about it. But now let's look at what A looks like if we change coordinates using this new basis, v1 and v2. You might ask, where did I get these vectors from? And that's a totally fair question, which I'm not going to answer right now. That's going to be a topic that we'll discuss in more detail toward the end of the semester. So for the time being, just go with me and be like, well, what if we did change coordinates to this new basis? Then, as we saw in the previous slide, the new matrix for A in terms of this new basis would be P inverse times A times P, where P is the matrix whose columns are the vectors in the basis. Since P is a 2 by 2 matrix, we can quickly use the formula for 2 by 2 inverses to calculate P inverse. So I'll let you double check this calculation. So now we have enough information to calculate this coordinate matrix for A. We just have to multiply P inverse times A times P. Now that's a calculation that would take you a couple of minutes to do, but I'll just tell you what the answer is. What you get is 2003. And what's nice about this is that this is a diagonal matrix. It only has non-zero entries on the diagonal, and it has zeros off the diagonal. And when you have a system of equations involving a diagonal matrix, then each equation just has one variable. So the variables are isolated, and you can just solve each equation for that variable, and you've solved the whole system.
Can I draw something?
Yeah, you can draw something at the end. So basically the idea is that when you use this different basis, then the matrix looks nicer and it's easier to solve the problems involving that matrix. But what does this mean? What did I just do? It'll probably help for me to draw a picture where you can see this coordinate matrix in terms of the original matrix A. So basically the idea is that instead of looking at the vectors E1 and E2 and seeing where they end up, we're looking at the vectors V1 and V2 and seeing where they end up when you multiply by A. And when you multiply A times V1, what you get is minus 4, 2, which is actually 2 times V1. And when you multiply A times V2, you get 3 minus 3, which is 3 times V2. And so the idea is that if you look at the matrix A from the perspective where you're thinking of V1 and V2 as being the axes, then A just has the effect of stretching those axes by different amounts. It stretches the V1 axis by a factor of 2, and it stretches the V3 axis by a factor of 3. And that actually gives us a simple but complete description of the transformation. So that's pretty cool. So like I said, the real value of this will become clear later on, but this is just to give you a preview so you can see how these things can be used. And this is a picture of a cloud with some blue sky around it.